Let's look at some weirder examples of making ions. Stuff where the octet rule doesn't really hold up the same way and things get a little bit dicey. You know, which way are we going to go? How is this going to work out? Okay, so let's look at something like beryllium. So let's take the shortcut. I'm going to draw up my scale here. Either get to 8 valence electrons by gaining or losing electrons. Right out of there. So 8, 7, 6, 5, 4, 3, 2, 1, 0, 8, 7, 6, 5, 4, 3, 2, 1. And this isn't really 0. Remember, if we lose all the valence electrons, we end up with a new set of valence electrons closer in to the nucleus. So we should end up with a set of an s orbital and a set of p orbitals in a previous energy level that should give us 8 valence electrons. Okay, so this is my valence electrons right here. Okay, so let's look at something like beryllium. All right, beryllium's neutral electron configuration is pretty small. It's pretty early in the periodic table. All right, it's atomic number 4, so it should have 4 total electrons. It's in the second row, second column of the s block, so it should end in 2s2. So 1s2, 2s2 is its electron configuration. Okay, so the farthest out energy level is the second energy level. It has 2 valence electrons. Okay, it's in group 2 or column 2 of the periodic table. So again, also just kind of a shortcut to double check, we do have 2 valence electrons. Nice. All right, so beryllium's Lewis dot diagram is going to look something like this. Be with 2 electrons, like that. All right, an ion must just, let's see. Are we going to gain or lose electrons here? Well, if beryllium is here with 2 electrons to start out with in its valence energy level, it's probably not going to want to gain 6 electrons just to get to 8. That seems like a lot of work. Instead, it would be a lot easier for beryllium to lose those 2 valence electrons it has to drop down to 8 valence electrons right here. Okay, so most likely beryllium is going to lose 2 valence electrons in order to become more stable. Okay, so what's going to be its charge? Well, it starts neutral, so it's got a charge of 0. We lost 2 electrons, so that means we're going to be subtracting -1 for each electron. So if we lost 2 electrons, that's -2 charge. So if we are losing 2 electrons, that's minus -2. That flips it to a positive, so our charge comes out to be +2. Okay, so once stabilized, this ion is going to be specifically a cation. It's going to be positive. Okay, if you ever can't remember which one's which, think cat ion. Cat. Cats are positive. I'm going to give little cat ears. So cations are positive. It's dumb, but it might help you remember it. If you need help remembering anions, you might think of it like this. All right. So A is A, N is negative. So anion is kind of like a negative ion. Now, is that really where the word came from? No, but it might help you remember it. It's kind of a little trick there. Okay, so once stabilized, okay, this is going to become a cation. So far, it's been a little easy up till now. We've lost 2 electrons. So we should be at 0 valence electrons, but we know that's not really how it goes. We're left with, kind of the energy level before. So, usually we end up with 8 valence electrons doing this, okay, just like how we drop down here. But if we look a little more carefully at our electron configuration we started with, 1s2, 2s2. If I lost 2 electrons, that means these guys would go away, and I'm left with 1s2. Haha, that is only 2 electrons. There are only 2 electrons left in this atom, period. Okay? And so those are going to be also my valence electrons. The farthest energy level out is the first energy level here, and there's only 2 electrons there. So this is not going to wind up with 8 valence electrons, but we did everything seemingly right. So let's play it out and see what happens. So as an ion, beryllium will have lost those 2 electrons, those 2 dots. Okay, and remember, we kind of do this backwards, where we write the number of the charge first and then, the positive or the negative. So it's 2 positive instead of plus 2. Or you can say 2 plus charge. Okay, or we could write it by showing all the valence electrons it actually has. So beryllium goes from having 2 valence electrons to having 2 valence electrons. They are 2 different valence electrons, but they are still 2 valence electrons. Just kind of odd. It seems like we did something wrong, because the number of valence electrons doesn't actually change. So did we mess something up, or is there something that we did right here? Well, what noble gas would we be like if we had this electron configuration? Okay, well, what has an electron configuration of 1s2? What are we mimicking? What is our role model here that beryllium is trying to be like if we lose 2 electrons? Well, if you go look at what has an electron configuration of 1s2, it is a noble gas. It's helium. Helium only has 2 total valence electrons. So it doesn't have 8 valence electrons, but it is at the end of the periodic table. It's over on the far right. It's with the noble gases because it's got similar properties. Okay, even though helium is kind of an honorary member of the S block and it should kind of be over there, we don't put it there. We put helium with the other noble gases because its reactivity is very similar. Sure, it doesn't have 8 valence electrons, but it acts in very much the same way. Okay, this is why we sometimes call groups families. Okay, because elements in the same column, the same group, the same family have similar properties. They act like each other. They behave like each other. They show similar characteristics and properties to each other. Okay, so helium is like neon and argon and krypton, where they typically don't like to make bonds. They typically don't react with other things. They're pretty unexciting on their own. They're lone wolves. So beryllium has successfully mimicked a noble gas. It's just not one that has 8 valence electrons. So it is still going to be stable by mimicking the electron configuration of helium. Okay, it doesn't follow the octet rule because it doesn't have 8 valence electrons. It has 2. So rather than octet, this is like a duet. Okay, so it does the same idea to stabilize. It is stable. Okay, it is more stable this way. Okay, it just doesn't hit that magic number 8. Okay, so you have to be careful. If you are dealing with small atoms, okay, this might not be 8 valence electrons here or here. It might be 2 valence electrons. Okay, so beware. Okay, helium is a noble gas, and it is just as valid at making something stable. As to kind of be a role model compared to the other noble gases. So be careful of that. Let's look at another example. Scroll down here. Nitrogen is pretty similar to some of the others we did, so we'll skip that one. Hydrogen, lithium. Okay, yeah, hydrogen is an interesting one. We'll do this one. I think that will give you enough to figure out the rest. Okay, so just like before, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, but we really know that's not 0. That's 8 valence electrons, usually for a previous row. And for small atoms, this may actually be 2. If we end up looking like helium, we're going to have 2 valence electrons rather than 8. So we'll have to be careful of that one. Okay, let's see what we got. Neutral atom's electron configuration for hydrogen is going to be Well, 1s1. Hydrogen is in the first row. It's in the first column of the s block. It only has one electron, period. So its electron configuration is just going to be 1s1. Real exciting. A neutral atom of this element has, it has one electron, period. So I guess that's technically got to be the farthest one out. So it has one valence electron. Just to check our shortcut, it's in group or family or column number 1 on the periodic table, which matches its number of valence electrons. Our shortcut still works. Okay, so our Lewis dot diagram for this might look something like this. Got big H for hydrogen, 1 dot, and I'm done. 1 dot for 1 valence electron. So, is this going to gain or lose electrons to become more stable? Well, this is a little odd. Hydrogen's right here with 1 valence electron. But this scaling doesn't really make a whole lot of sense because of how small it is. If we're going to have 2 valence electrons when we're gaining electrons or losing electrons, the scale doesn't really work anymore. It's more like this. Okay, and maybe we should just redraw it. And maybe the scale isn't even a great idea to work with as it is. Maybe let's just play it out as it is, and we'll see. Okay, so how do we make hydrogen happy? Well, regardless of this shortcut scale thing we're drawing on the right side, the goal is to get hydrogen to be like a noble gas. Well, what's the closest noble gas to hydrogen? Well, helium is right after it, and helium is a noble gas. So maybe what we should do is focus on how do we get hydrogen to be like helium? Well, if we start with 1 valence electron, how many valence electrons does helium have? Well, it's in column 18, but it doesn't have 8 valence electrons. It has 2 valence electrons. Okay, so if we could get hydrogen to gain 1 valence electron, that would put it at 1s2, which is the electron configuration of helium. So that seems like a pretty good deal. So hydrogen is going to gain 1 valence electron, okay, in order to become more stable. Started with a charge of 0, gained 1 negatively charged electron. That leaves us with a charge of -1. Okay, so this anion is going to end up with 2 valence electrons, the one it started with and the one it gained. So our Lewis dot diagram is going to look something like this: H dot dot. You can put those anywhere. Okay, and we have a -1 charge. So if I want, I could put it as just a negative sign. You could also put it as a 1 negative. Remember, number goes first before the positive or the negative. So 1 negative, but it's kind of implied. So a lot of times you'll just see the negative sign alone without that. Okay? So this doesn't follow the octet rule. Okay? It's kind of a weird example in that sense. But is this the way it should go? Again, the scale didn't really help us in this case because we're dealing with such a small number of valence electrons. Helium is a noble gas, very close. We only had to gain 1 valence electron to become an anion, a negatively charged version of hydrogen. And it seems better. It seems more stable this way because it's like helium's electron configuration. But this isn't the only way you'll see hydrogen. You could also, fairly enough, say, if I'm starting with 1 valence electron, I could either gain an electron to have 2 valence electrons like what we did, or maybe we lose an electron to have 0. And this isn't like a backup to a previous row thing. There is nowhere to back up to for hydrogen. So it would actually be 0 valence electrons. This does happen. So an alternative to this would be to make something a little bit different, where we lose 1 valence electron. Okay, and so we end up with a charge of 0 minus -1, which equals +1. Huh. right? That would mean it's a cation instead of an anion, and it has 0 valence electrons. All right, so its Lewis dot diagram would be H, and it just straight up has no dots, no valence electrons. And it has a positive charge, so you could either, again, write 1 plus, or you could just write plus, to show it's a positive 1 charge. The 1 is implied. Okay, and in this case, it wouldn't be like any noble gas. It has no valence electron, so it's not mimicking anything. But this does happen. So this option in blue, where hydrogen gains an electron, seems like the best option because we do what we expect. We end up mimicking the electron configuration of a noble gas, even though we don't hit that kind of magic number of 8 valence electrons. But as you go further into chemistry, you'll also come around to find this ion quite a bit. It's a pretty popular ion. So it's a little strange. Okay, this is an example where I would take either answer, either gaining 1 electron or losing 1 electron, and it's totally valid. And in either case, it's not going to follow the octet rule. Okay, based on the kind of way we've been working out these problems, being like helium and gaining 1 electron seems like the better choice, but losing an electron is equally valid as an answer. So most of the questions you'll get in my class are not going to be these kind of weird, crazy ones. And hydrogen really is probably the weirdest one you'll come across in kind of an introductory chemistry class. So don't look at this and sweat it and be like, oh, I'm going to have to try and figure out all these weird things. No, most of them are going to be pretty straightforward. Okay, but this is just to show you that there's always something new and different and weird in chemistry, and sometimes we have multiple options for how something can become more stable and can become lower in energy. So this is just one option. The other examples here that we could look at, like nitrogen was up here, okay, is going to be a little bit easier. So nitrogen should end up following the octet rule if you do this right. Below hydrogen. Lithium does not follow the octet rule, but it should be a little bit simpler than the hydrogen example we saw above this. Okay, so hopefully seeing kind of those harder examples will make the other problems to do a little bit easier. Hopefully this won't be so awful to kind of tackle all at once.